Is it visible?
Your screen is visible, but your voice is not clear enough. Maybe some.
Now is it okay? Like,
Yeah,
can you
yeah,
hear me clearly?
it's better now.
Okay, so like you mentioned, so for the past year, for the last 1 year, I have been working on this quantum computing and its application, mainly as a part of my master's thesis. Uh, and as my supervisor, Dr. Ankira is a high energy experimental physicist. So my motive was to use this quantum computing in some high energy problems, maybe mainly a nuclear problem, which I have chosen in this part. So the topic is like quantum computing in many body physics, and yeah, so let's get started. The outline would be like this. So first I introduce the concepts of quantum computing. Then I tell you how a physical qubit can be realized, and then comes the main part of my project, which is the deutron problem, using which like it is the core of my project, and I have used different quantum computing algorithms and techniques to find the energy spectrum of the deuteron problem. Like variational quantum eigensolver and subspace search variational quantum eigensolver. These are the two techniques which I've used to find the energy eigenvalues of this deuteron problem. And then I would discuss briefly about quantum noise and its impact on my simulation. And I would then discuss about a new model type approach which I have been thinking of late, which can be useful if I want to go from deuteron to a heavier nuclide, and then summary and outlook. And this thing, future outlook, this thing I would not discuss over here. Okay, so firstly, the basic building blocks which differentiate between a classical computer. By classical computer, I mean a conventional computer which we are using these days. Is a bit and the qubit. Qubit means quantum bit, which is the basic building block of a quantum computer. So in classical bit, we can have either the state 0 or 1. So it is always a binary state. Whereas in quantum computing, we can have a superposition of state 0 as well as we can have the state 0 and 1, as well as we can have any superposition in between. Like 0 plus 1 by root 2 is also a valid state of a qubit. That is, there is a spectrum between 0 to 1. So this superposition is a key which is giving.
Debankan, sorry to interrupt you. Can you keep your microphone closer to your mouth? Because voice is, there is some issues with voice.
Maybe
audio.
you can try without earphones. I think
yeah,
it's
maybe you
getting
just
your
remove
voice enough.
Actually, sir, I'm using a laptop. Like I don't think
Okay.
it would be good.
Okay. Yeah, keep it closer. Maybe try keeping it closer to your mouth while you speak.
Is it better now? Like
there is echo. There's a bit of an echo now. So yeah, but it looks like it's a microphone problem. It is this this problem.
I think you can try without. It works on laptop. It works always better without the earphone. So maybe you can give it a try, and if it doesn't work, then you can switch on your earphone stack.
yeah, okay. Can you hear me now?
Yeah, I think it.
Yeah, now I think it's better. It's better.
Okay, but I cannot hear you guys properly. Okay, let me try.
You don't have to hear us, so you just speak.
Okay, so what I was telling is that this superposition and another concept which is entanglement are the key features which gives quantum computing the upper hand over conventional computers. Say for example, if I have 3 coins and I toss the coins, so there can be 2 to the power 3 8 configurations of heads and tails. So if I use classical bits to store all the 8 informations, I will be requiring 8 classical bits. That is 2 to the power 3. So in that sense, it is an exponential scaling. But if I use a qubit to store all the 8 informations, I can just use 3 qubits, because 1 qubit can be in any of the states 0 and 1. So 3 qubits can store all the 8 informations of the 3 coin tosses. So by this I mean that the concept of exponential scaling can be mapped to linear scale when we are using a quantum computer. So this is the advantage which people are trying to explore in quantum computers and to solve problems which classical computers find difficult to solve. Okay, so another elements which are important when we're using a simulator or quantum computers is the quantum gates. So quantum gates are nothing but unitary matrices which converts one qubit from a state to another. Like a unitary matrix, we operate it on a state of a qubit and it gives us an output state. So here you can see in this picture, I have shown few examples of quantum gates, which are Hadamard gate, Pauli X, Pauli Y, and Pauli Z. These are very important gates. That's why I have shown them here. And the corresponding matrix representations are like this. All of these matrices are unitary because ultimately we have to preserve the norm of the state after we apply unitary matrices. So now here I have shown quantum circuit. So the initial state, I have taken two qubits. Both the qubits are in the state 0, 0. And then I apply a Hadamard gate on the first qubit, followed by a C0 gate, entangling both the qubits. So the output state is of the form 0, 0 plus 1, 1 by root 2. And here you can see that the state 0, 0 and 1, 1 both are having a 50% probability of occurring. So if I make a before I make a measurement, the first qubit and the second qubit both have a 50% chance, because if I take the modular square, it will be half. So 50% chance of being in state 0 as well as in state 1. But suppose I make a measurement and I find that the first qubit is in state 0, that means the quantum state has collapsed to 0, 0 state. So now I can say surely that the second qubit will always be in state 0 and it can never be in state 1. So the probability changed from 50% to 100%. So this entanglement I'm discussing here because entanglement finds a application in quantum teleportation, and also in the later parts you will see the techniques of ansatz building also uses entangling gates between qubits. Okay, so this is a quantum circuit. So Q0, Q1, Q2, all these things are qubits. After that, we apply a sequence of gates, which are the unitary gates. And this plus sign, this one is a entangling gate. This is a 2 qubit gate. And after that, this meter symbol, these are all measurements. So we have an initial register of qubits. Then we do some operations, that is we apply some sequence of gates, and then finally we make the measurement of the qubit. So this is how a quantum circuit looks like. Okay. So now let me discuss about how we can physically realize a qubit. So any two-level physical system can be approximated as a qubit. Like we can treat the ground state energy and the first excited state energy of an atom as the two levels of a qubit. So we can say the ground state as the state 0, and we can treat the first excited state as the state 1. Also, we can treat the two polarizations, that is vertical polarization as state 0 and horizontal polarization as state 1 as the two states of a qubit. And the third picture shows that we can also treat the spin orientation of an electron as the two states of spin, as the two states of a qubit. That is, if the electron is in upspin state, we can treat it as state 0, and if it is in downspin state, we can treat it as state 1, or vice versa. So two most popular techniques which are used for qubits are ion trapping, which is mainly used by companies like Honeywell, and another famous technique is superconducting qubits, which is used by IBM itself. So I will be briefly discussing how we can trap an ion and we can use it as a qubit. So for trapping an ion, what we need is a bunch of calcium atoms. The reason for choosing calcium atoms is calcium has 20 electrons. So 20 electrons, so 2 electrons are in the valence shell, and we can kick out one of the electron by using a laser. Now, once I kick out one of the electron, it becomes an ion, it becomes a positively charged ion, Now we can apply a arrangement of electrodes. So here you see this thing is a electrode here, and we keep on changing or flipping the signs of the charges of the electrode plates. So in that way, as like charges repel each other and unlike charges attract, that will cause the ion to be trapped in a position in the center. So here in the center, you can see the ion is trapped, the calcium ion is trapped. So this is the original picture. Here the 4 dots are 4 trapped ions. Now once it is trapped, the outermost electron or the valence electron has an intrinsic property called spin. So we can use a microwave with an oscillating magnetic field, and we can tune it in such a way that we can change the direction of the spin, because ultimately the spin will align with the direction of the magnetic field, and we can stop the magnetic field in such a position that we can create a superposition state. Like we stop the spin in such a state that a superposed state of 0 and 1 is created. In this way, the ion is trapped and we can use it as a qubit. Okay. So now comes the main part of my problem. So I've chosen this deuteron problem. So I have chosen this deuteron problem because this was the simplest problem to study the nuclear-nuclear interaction. And this Hamiltonian I have taken from this reference paper, and you can see that this Hamiltonian is in second quantized form, where n is the harmonic oscillator basis. Now this Hamiltonian actually comes from effective field theory calculations. We will not go into that detail, but my starting point was this Hamiltonian in harmonic oscillator basis with the values V0 as mentioned here in the paper, and the value of h cut omega is 7 mega electron volt. And these two are the matrix elements of the kinetic energy and potential energy. So I will use this thing, and then I will use the two techniques, variational quantum eigensolver and subspace search variational quantum eigensolver, to find the ground state energy of the deuteron problem. Okay. So before I discuss how I use variational quantum eigensolver, let me first discuss what variational quantum eigensolver is. So in quantum mechanics, we have a variational principle where the concept is like we can take any acceptable wave function as, say, for example, a exponential of minus bx squared. So this is an acceptable wave function. And for Hamiltonian, in which we cannot directly find the energy eigenvalues, we can use variational principle to approximate the eigenvalues. So what we do is we find the expectation value of the Hamiltonian, and then we try to minimize it with respect to the free parameter, which in the case of the wave function was the free parameter b in the exponential. So we find del expectation value of h, del b equals to 0, and from that we find the value of b for which the eigenvalue is giving us a minimum. So here also we use the same concept, but instead of using any parameter b, we are using the arbitrary rotation angle of the quantum circuit as our free parameter. So if you look at this circuit here on the right hand side, we initialize the state of the qubit as psi of 0. We can treat it as a qubit register starting in the state 0, 0. And then what we do is we apply some unitary gates like ry theta.
Debankan, I just want to make a quick comment here. For those of maybe in audience, we have students from physics or maybe undergrad students. So I think they are familiar with this. They would have seen in textbooks this expectation value. You have a Hamiltonian, then you have a wave function, and you take an expectation value with reference to that. But in quantum mechanics, we typically calculate it either analytically using some mathematical techniques, or you use some approximation methods to calculate it using perturbation theory or something. But here what Debankan is trying to do is using this VQE, he's trying to, we calculate it on a quantum computer. So that is the main difference which Debankan has worked on. That the question is how can you evaluate this expectation value of a Hamiltonian and calculate the ground state energy of that Hamiltonian on a quantum computer. And when you say on a quantum computer, you will have to write quantum circuits, as Debankan is explaining over here. So, but the main thing is, main objective to calculate is this expectation value. Fine, Debankan, you want to add something on that? Am I right?
Yes, sir. Like the main part here is to calculate the expectation value, like which in quantum mechanics we calculate as Psi dagger. Then we put the operator in between and then Psi, and then we integrate over the space we want to find the value. But here what we are doing is the wave function, here we call it as ansatz, and that is a parameterized wave function, which is depending on the parameter theta. And theta is the arbitrary rotation angle by which we are rotating the state of the qubit. So see here in the right hand side, ry theta means this is a rotation gate about y-axis. So if I have a qubit which is having a spin in any direction, say along x direction the spin is oriented, we rotate the state of the spin by an arbitrary angle theta about y-axis, and then we get a state which is depending on theta. So u of theta is that unitary evolution, or u of theta is the unitary matrix which is applying on Psi of 0 to give us Psi of theta. Now you see the state of the qubit is depending on the parameter theta. Just like in our variational principle, the wave function was depending on a free parameter, as I said, exponential of minus b. So here the free parameter is theta. And now what we will do is, we have our Hamiltonian. Like in the previous slide, I have shown that the Hamiltonian was there in the harmonic oscillator basis. So what we do is, we find the expectation value of the Hamiltonian with respect to this parameterized ansatz. So wave function, I am calling it as ansatz. So you see that the expectation value is depending on theta now. What we have to do is, now the technique is that we have to vary the value of theta to find a theta which is giving us a minimum expectation value. That is, we have to optimize the value of theta in a space and find the value of theta which gives us the expectation value of the Hamiltonian as the minimum energy eigenvalue. So that is what the variational principle says. So here you see in the workflow of DQE. Okay, so on the right hand side, I have two more pictures. So this thing I have shown here just to show that the first circuit on top is a 2-qubit circuit. If we are having a Hamiltonian which depends on, like, that is a 1-to-1 mapping. If you are having a Hamiltonian which is a 2-qubit Hamiltonian, for that we use a circuit in which we have 2 qubits initially. But if the Hamiltonian is a 3-qubit Hamiltonian, then we have a 3-qubit circuit, and so on. Like, we can build a circuit depending on the number of number of qubits in the Hamiltonian, which will be more clear in the next slide, as I will show you. So here is a workflow of VQE, or Variational Quantum Eigensolver. So this is a hybrid technique. That is, we use both quantum computing as well as classical computing. So for the quantum part, what we do is, we prepare the variational ansatz Psi of theta, and then we take the expectation value of the Hamiltonian with respect to that Psi of theta. So here you see there is something like a tensor product of j equals to 1 to n. So this is just showing the Hamiltonian in the Pauli operator form. So sigmas are the Pauli operators, and we take the expectation value. Now we have this thing, expectation value which depends on theta. Now what the classical computer or optimizer does is, it changes the value of theta, or it optimizes the value of theta in a direction such that we reach a value of h of, that is, the expectation value of the Hamiltonian is now a minimum value. So that is our ground state energy. So the classical optimizer, say we start with a value of theta 1. So for theta 1, the expectation value is calculated and we find the value. Now the classical optimizer changes the value of theta 1 to theta 2, and again we find the expectation value with respect to theta 2. In such a sense, the thetas are varied and we find the value for which the expectation value is minimum. So that is our ground state energy. Okay. So now the Hamiltonian is always given as an input to this quantum computer for finding the expectation value. Now the Hamiltonian which I have shown in the first slide, it was on the harmonic oscillator basis, or a second quantized Hamiltonian. A second quantized Hamiltonian means it has this creation and annihilation operators. So this cannot be directly given as an input to the quantum computer, because quantum computer won't understand this language of creation and annihilation operators. So we have to convert it to a convenient form which can be understood by a quantum computer. So for that, we have a technique called Jordan-Wigner mapping. So what Jordan-Wigner did was, so long before quantum computer was even conceptualized, they had shown that there exists an isomorphism between this creation and annihilation operators and Pauli matrices. So the Z, X, and Y, these are all Pauli X, Z, and Y matrices. So there is a isomorphism existing between these two, and we can have relations which connect both of them. So I have used these relations, and I have substituted these matrix elements of T and V into this equation. And the final form of the Hamiltonian, which can be given as an input to the quantum computer, looks like this. So H3, so 3 means this is a 3-qubit Hamiltonian. Okay. So H3 is a 3-qubit Hamiltonian. And so the first term is an identity. That means we will be using an identity operator. And then the second term is Z0. So Z0 means there will be a Z matrix operating on the 0th qubit. 0th qubit means the first qubit, and so on. So the subscripts denote the qubit on which the gates are acting. So we have successfully converted the Hamiltonian from second quantized form or creation annihilation operator to a form which can be well understood by the quantum computer in the form of Pauli matrices. Okay. So here I have shown how the different Hamiltonians looks like H1 is a 1-qubit Hamiltonian, and so on, H2, H3, H4. So H4 is a 4-qubit Hamiltonian, and you see, as the numbering was that as I keep on increasing the value of n, the number of qubits in the Hamiltonian, the number of terms keeps on adding, and we reach closer to our experimental value, which is minus 2.22 mega electron volt. So around 5 qubit, you see it is minus 2.18 mega electron volt. Okay. So after I found the value which was very closer to experimental value, what I wanted to do was I tried to explore various VQE components. That is, there exist different types of entanglement pattern as well as mappers. Like for mappers, I use Jordan-Wigner mapper. And there are also various types of mapper which are known as parity mapper, Braviki type. So these are various components which are available in this kit, IBM. So I took combinations of all of them to see for which combination we are getting the ground state energy faster. Like we are changing the value of theta, right? We are changing the value of theta each time to give us an optimum result. So which combination takes least amount of time to reach to the converging, or which optimizer is, or which combination is taking the least amount of iterations to reach the reference value. And from what I find was that Jordan-Wigner, when it combined with real amplitude and circular entanglement, this gave us the best result. So our decision of using Jordan-Wigner mapper previously was a correct decision. So this is just a comparative study which I've done. So after I explored VQE, another technique which I wanted to explore to find the ground state energy of deuteron was Subspace Search Variational Quantum Eigensolver, which is also known as SVQE. So this is based on the concept that every Hermitian matrix or every operator in quantum mechanics, the eigenvectors corresponding to different eigenvalues are always orthonormal to each other. Okay. So, and another concept which is important is, suppose we have a set of orthonormal eigenstates, and after we perform some unitary operations on all of the states in that space, we get output states which are orthonormal to each other. What I mean is unitary transformation always preserves the orthonormality of states. So psi of 0, phi of 0, phi of 1, all these things are orthonormal gates. So phi 0, phi 1, phi 2, these things are all orthonormal to each other. And after I apply u of theta over it, I get E0, E1, E2, all the states of the eigenvalues, all the eigenstates corresponding to different eigenvalues, which are again orthonormal to each other. Say for instance, if you think of the harmonic oscillator, so the ground state energy of harmonic oscillator is a cos function, and the first excited state is a sine function. So both of them are orthonormal to each other. So what I have done is from VQE, I get the ground state energy and say phi of 0 is the ground state energy eigenstate. Now I create a set of orthonormal states which are orthogonal to phi 0 by Gram-Schmidt orthonormalization. And then what I do is I give it as an input to the unitary circuit, and each of them has a VQ decomposition of their own and maps them to each of the energy eigenvalues. Say phi 0 maps it to the ground state, phi 1 maps it to the first excited state, and so on. So I have used this concept in deuteron also to establish some meaningful inferences. So before I move into my results of deuteron, I want to show you an example from this reference, which is a 2019 paper. So here they have used the concept of SSVQE. What they have done is they have taken this transverse Ising model Hamiltonian. So here you see the Hamiltonian depends on x, z. So x and z are the Pauli matrices acting on the ith and jth qubit. And they have used the concept of SSVQE to plot the ground state energy, first excited state energy, second excited state energy, and third excited state energy. So on this plot, you see the dotted lines are the reference values, and the bold lines or the curves are the simulated graphs. So after a certain number of iterations, the bold lines are converging with the dotted lines, which means that each of the orthonormal states which you have chosen as input are finally mapping to the output orthonormal states, which are nothing but our energy eigenvectors. And also they have plotted fidelity. Fidelity shows the measure how one quantum state is close to another. Like if you see, fidelity is defined as bra of EI, then U theta, then K of phi I. So this is, and then we take a modulus square, that is in the output we want this EI, so it is kept in the bra of that, so bra EI, and in the Kate we have phi of EI. So this is our input state, and if fidelity is equals to 1, that means our input state is mapping to our expected output state. So here in this plot you see after certain number of iterations, the solid curves are converging in the dotted line which is corresponding to fidelity 1. So all our input orthonormal states are mapping to our expected energy eigenstates. Now this was an example which was there in this paper. So I used this concept of SSVQE and I applied the code and the concept in my deuteron problem to see what the result we get. So I have varied the number of qubits in the Hamiltonian, and the second column shows the ground state energy in mega electron volt. So here you see the ground state energy values exactly matches with the VQE calculations. All of the energy values are negative, that is minus 0.43 and so on. So a negative value means the system is bounded, and we know that the deuteron is a bounded system. And as we move to the first excited state, we see all the results which we are getting are positive. Okay. So from this, I infer that positive eigenvalues of energy means the system is unbound. And we know from physics that deuteron, the only stable state or the bounded state of deuteron is the ground state. And once it is excited, it is no longer bounded and it becomes a free neutron and a free proton. So this is maybe matching with the fact that there is no excited state of deuteron. Only energy state which is possible for deuteron is the ground state energy. That's why all the energy values are coming positive. Okay. So up till now, what I was doing was a perfect simulation. That is, I was considering an ideal case where I did not consider any noise from the surrounding. But in reality, all the qubits are noisy because whenever there is a system, it interacts with the environment, and there is some unwanted interactions with the environment. And in quantum information, these things are called noise, quantum noise. So that tampers with the that interferes with our results, and it has a significant impact on our results. So I wanted to show how this quantum noise is impacting our results. So this picture here shows the ellipse in the blue color is our system, and it is exchanging information with the environment, and the entire thing can be considered as a universe which is isolated. Okay. And for example, if a state of a qubit is represented by two positions of an electrode, and then the unwanted interaction with other charged particles, that is, the electron can interact with other charged particles which are present in the surrounding, that can change the orientation or the position of the electron. So that will change our state of the qubit, and we might not want that to happen to our system, because for a stable amount of time, or for a sufficient amount of time, we want our qubit to be in a stable state. So if our state is changing, that means there will be some error in our simulation. So I wanted to see how that is taking place. So for knowing how a quantum noise is acting on our system, this quantum operator formalism is very useful. Like if we are dealing with ideal quantum systems and we want to explore the continuous time evolution, the only equation which we use is Schrodinger equation. Okay, where there is a unitary, and we see how there is a quantum dynamics of the system is studied using Schrodinger equation. And for quantum open system, when there is a interaction with the environment, the equation which we use is Lindblad-Masters equation, which shows the continuous time evolution. But if we want to study how the system is changing discretely, that is, we do not want to have a continuous time evolution, we want to see how it is changing discretely, then what we use is this quantum operator formalism. So this rho prime is equals to epsilon rho. So rho is our input state, and epsilon is some quantum operation which is acting on rho to give us output state rho prime. Okay, so this epsilon of rho can be any unitary operation or can be any measurement. So measurement I have shown by capital M, and there is a subscript M. Now what we want to do is we want to take into account the interaction with the environment. So that's why I've started in a state which is rho tensor product with rho ENV. So ENV stands for environment. So this is our product state, which is a combined state of the system of interest and the environment. And we are considering that there is a unitary evolution, which is U and U dagger. That is the environment, or the universe as a whole is undergoing a unitary evolution. And after that, what we do is we trace over the environmental degrees of freedom. So once we trace over the environmental degrees of freedom, we are left with the reduced state of the system alone. That is, we have taken into account the interactions with the environment. Now we can study our principal system. Okay, once we do a partial trace over the environment. So this thing I have done, and this I have just shown the calculation. That is, for tracing, I have taken the orthonormal basis of the environment. Then I did a sum over that orthonormal basis. And this E0, bra E0, K T0, or K T0, bra E0 is the initial state of the environment. And finally, epsilon of rho looks like this: summation over K, Ek, rho, Ek dagger, where Ek are the Krauss operators. So these Ek are called Krauss operators, which is the operator which is acting on the principal system alone and takes into account the interaction of the environment. Okay. So this thing we'll be needing in the next slide. So that's why this form is important: Ek, rho, Ek dagger. So another thing which is important before I discuss about quantum noise is how a qubit or a single qubit operation is represented geometrically. So here you see on the right hand side, this is a Bloch sphere. Okay. So every state on the surface of the Bloch sphere, or every state of a qubit, can be represented as this: rho equals to I plus R dot sigma by 2, where R is the real 3-component vector and sigmas are the Pauli matrices. Okay. And it can be shown that every state on the surface is a pure state, whereas as we go towards the center of the Bloch sphere, the states becomes mixed state. So the purity is less as we go from surface to inside of this Bloch sphere. And what happens is, when we apply some gates, what happens is this state of the qubit rotates in this Bloch sphere. Okay. So this thing is important, as I will show in the next slide. So I explored two quantum noise channels. First is a bit flip channel, and the second is a depolarizing channel. Okay. So bit flip channel means as I told you, the qubits can be in a state of 0 as well as 1. So bit flip channel does is it changes or flips the qubit from 0 to 1 with certain probability, and it keeps it unchanged with probability p. And I can show that the Krauss operators for these channels are represented by this thing: E0 and E1. So E0 and E1 are the Krauss operators which are acting on this system, which takes into account the effect of the environment, which is flipping the bit from 0 to 1. And on the block sphere, the impact is shown like this. As you see on the E1, there is this X matrix. Okay. So X matrix commutes with X matrix, Pauli X commutes with Pauli X, but it anti-commutes with Pauli Y and Pauli Z. So that's why the polarization vector along X direction is unchanged in the final state, whereas in the Y and Z direction, it is shrinking. So this perfect sphere, which was representing all the pure state, after the noise channel has acted on it, is converted to a mixed state where it is converted to a ellipsoid. And there is an anisotropic, anisotropically it is getting deflated along different directions. Okay. But along X direction, it is remaining unchanged. The polarization vector along X is unchanged. And another thing is we can say that this can even go outwards also, but that is not possible. That is, this sphere cannot go outwards because we know from quantum mechanics that trace of rho square should always be less than equals to 1, which implies that modulus of r square should be less than 1. So that means the length of the vector can only go or can only decrease. So it can only go inwards, it cannot go outward. So this is one channel for which the Krauss operators are like this. And another channel which I explored for quantum noise is a depolarizing channel, which says that with probability P, the qubit is converted to a completely mixed state. Okay. So for completely mixed state, as you know, the trace would be half for a two-dimensional system. And with probability 1 minus P, the qubit is left untouched. And here with some simple calculations, I have shown that the Krauss operators for this channel can be represented as this: root under 1 minus 3p by 4 I, which is identity matrix, root p by 3x, root p by 3y, and root p by 3z. So x, y, and z, all three Pauli matrices are acting as Krauss operators. So there is a shrinkage along all directions, and we see that the sphere is shrinking isotropically. So this is the effect of depolarizing channel for probability 5%. Okay. So with 5% probability, there is a depolarizing noise which is acting on our qubit, and it is changing the states to a final state which looks like this on the block sphere representation. Okay. So this was theoretically how we can implement a quantum noise. Now I implemented this on my simulation. So before I implemented my noise models of bit flip and depolarizing, there is a fake noise model which is mimicking the data from real hardware. Okay, so IBM has this facility that in real quantum hardware there are some noises, and it has exactly the data of the noise which is there on a real hardware, and we can use it in our simulation to see how our results are changing. So if you see in this table, the first column is the number of qubits in the Hamiltonian, and the second column is when there is no noise on the simulation. So the results are perfect. All the results are coming negative, and it is approaching the experimental value of minus 2.22 mega electron volt. So for 4 qubits, I've shown it is minus 2.14. But as I am using a noise from this fake noise model, I am getting the first result as negative of minus 0.40, whereas all the other three results are coming positive. So that questions our concept that deuteron is no longer bound in the ground state. But we don't have to worry about that because these are all noisy results. And if I use some quantum error correction techniques or quantum error mitigation techniques, this can be refined to give us our results, which will be again be negative, and which will match with the fact that deuteron in the ground state is a bound system. So to see that my simulated results are actually not wrong, what I did was I sent my code to IBM to execute it in a real hardware, and for 3 qubit I have done it. And you see for the first two cases, for qubit 1 and 2, I am getting negative results, whereas for third qubit I am getting a positive result. So that shows that my simulated value of getting positive results is indeed not wrong. In a real hardware also we are getting same positive values. Okay, So after I did this thing, I tried to implement my bit flip noise model and depolarizing noise model in my simulation. So what I saw was that except for the first qubit result, which is minus 0.41, all the results are coming positive. And as I increase the number of qubits, the thing is diverging more and more. Okay, there is a significant difference between the expected value and the real value as I keep on increasing the number of qubits. Now, the reason for this is, suppose there is a single qubit, so the impact of noise on that will be less. Now, if I have multiple qubits, all the qubits can have a certain probability with which the noise model is acting on it. And so the deviation from the reference value will be more on increasing the number of qubits. So this same trend is followed when I use a depolarizing channel with 5% probability. Okay. So this is how, this shows how we are getting the results which are positive in a real quantum hardware, but we don't have to worry about that because with proper error mitigation technique, we can get the results which will eventually boil down to realistic and meaningful outcomes. But that was beyond my scope, so I did not explore it here. So once I was done with deuteron, I was thinking that how I can approach a nuclei with more number of nucleons, because as I increase the number of nucleons, there will be more interaction terms, and the potential energy matrix elements will be very difficult to find, because for two nucleon it is easy because there are two nucleons acting with each other. But as I increase the number of nucleons, it will be difficult because for many body interactions we have to take into account that EFT calculations and so on. So I thought that maybe we can use a model type approach to deal with heavier nuclei. So when I was thinking over this, I came across a paper in Nature Communication where they were treating alpha as a building block of some of the nucleus as beryllium and carbon. So they thought that alpha was the building block of beryllium and carbon. And then they tried to explore the physical quantities or the physical properties of these elements. And then they found that they were matching or were having certain amount of agreement with the experimental data. So I took this concept and I thought that maybe I can use deuteron as a building block for helium, because deuteron has one neutron and one proton, and helium has two neutron and two proton. So what I can do is I can treat two deuteron and I can use it as a helium. Now from shell model calculation, it can be shown that the angular momentum quantum number L is equals to 0. So there is no change in the expectation value of the kinetic energy term. It is same as that of deuteron problem. The only thing that changes is the potential energy term. Okay. So here in this picture, you see this NP, this is neutron and proton. So I think of two deuteron making a helium nucleus. So now the number of nucleon is 4, and for 4 I can make 6 pairs if I take a combination 4C2, because all of them will be having strong forces among each other. So the effect will be same, and I changed the value of V0 to 6 times of that. Okay. So 6 times of that is changed, and then I did this exact same thing as I have done for deuteron. A note here on this green box, the experimental value of helium ground state energy is minus 28.3 mega electron volt. And in this table, you see, as I kept on increasing the number of qubits, around 6 qubits, we have minus 26.69 mega electron volt, okay, which is very close to the experimental value. So although this thing is not exactly same as that of experimental value, as a thing we were getting in deuteron, like there the deviation was very less. But here one thing I can say for sure is that the range is very optimistic. Okay, like minus 26.69 is very close to minus 28.3. So this idea of my model can be used, and I will explore this in future to see if I get more accurate results. So I just wanted to discuss this before ending my talk. And finally, I would like to give you a summary. So what I've done is I've created a variational circuit for ground state, and then I encoded the Hamiltonian using Jordan-Wigner to convert it to a form which is easily understood by quantum computers. The results of deuteron problem were indeed very satisfactory. Then I explored the concepts of quantum noise to show how quantum noises in real world are affecting our simulation. A meaningful inference about the excited state of deuteron was made, where I showed that all the excited state values were coming positive, which matches with the fact that deuteron in its excited state is an unbounded system. And then I thought of this model type approach in my project, which has a range of results which looks pretty optimistic and opens door for my future work. So I've done this to show that two-body problems can be solved using a quantum computer. Now, more powerful quantum computers with more stable qubits are coming, are already being fabricated and coming in future. So that can be used to solve many-body physics problems, where classical computers takes exponential amount of resources and it takes a long time and becomes very difficult for conventional computers to solve these problems. So maybe soon we will have quantum computers and it will show its supremacy. So I hope in future I will be exploring these things. So quantum computer indeed shows a very realistic and optimistic future when it comes in exploring physics and chemistry problems, and even in other branches like finance and medical sciences. So before I end this talk, I like to acknowledge few people. Like firstly, I'm very thankful to my supervisor, Dr. Anki Roy. Like she is an experimental high energy physicist, but her motive was always to explore new things. That's why she insisted that I should explore this new branch of interdisciplinary studies. And then I would like to acknowledge two other people, Dr. Debojyoti Sarkar and Dr. Debankan Das, who are members of my research committee. And finally, three people with whom I have been working of late, and Dr. Mohsin sir and Mr. Basit sir, they have been very kind to me. And whenever I had any problem in theory or in coding, I always discussed with them. And finally, last but not the least, is Dr. Ruksan, who is working in IBM Quantum. He always discussed or helped me whenever I had any doubts in quantum computing. And I would like to thank my lab mates. Yeah. Thank you all.
Thank you, Debankan, for this wonderful talk. I think it was a very